All right. Hello, everybody. The broadcast is said to be live now. I hope it's recording well. I am Dr. Frank Summers of the Space Telescope Science Institute, and it is my pleasure to welcome you to celebrating 23 years of the Hubble Space Telescope. We had
Yay!
yay! We have some amazing things, and let me just show you a couple things. What we're celebrating is that 23 years ago, this was the launch of the Hubble Space Telescope on the shuttle mission STS-31. And you'll notice that not only do we have Hubble launching on Discovery here, we also had just happened to have another another shuttle on the launch pad doing some testing. And then a day later, we had Hubble was deployed by the astronauts of STS-31. And we have 23 years of amazing history of images. And today we are going to discuss the image that we released last Friday night. Friday morning, sorry, an infrared view of the Horsehead Nebula. This is the image here, and this is the amazing image that the experts who processed it will tell you all about it. So let me stop my screen share. There we go. And introduce the experts who are going to talk about it. Our first expert here today I'm going to introduce is Mr. Zolt Levay. And Zolt, why don't you tell them a bit about your history here, what you do at Space Telescope.
Okay, thanks, Frank, and welcome everybody, and happy birthday. Happy birthday, Hubble, and happy Earth Day, all those things. So I started here at Space Telescope Science Institute quite a long time ago, about 30 years ago. And for the last many years, I've been producing images from Hubble data. So that's kind of what we do. We use the same data that the astronomers use and have produced quite a number of nice, colorful images to distribute to the public to demonstrate what Hubble's doing to announce the science discoveries from Hubble. And I'll turn it over to Jennifer Mack.
Hi, I'm Jennifer, and I've been at the Institute here for about 16 years. I do both science research and instrument calibration for the telescope, and I'm a member of the Wide Field Camera 3 team. That's the camera that was used to make the observations that were made today, that we're presenting today. And so I'll be giving you a bit of a more technical view of behind the scenes. How do we take these images that come down from the telescope, raw images, and put them in together to then create this beautiful color composite that you see in the news.
Right, and so as you can see, we're going to be taking you, not just give you the pretty picture overview, but we're going to give you the technical behind the scenes of how these images really are put together. So Zolt has put together a PowerPoint presentation, so if he'll turn on his screen share, we'll go back to Zolt, and Zolt, take it away, tell them all the cool stuff.
Okay, thanks, Frank, and I'll get my thing started here. I will start the slides. So as Frank mentioned, we're talking today about this new image from Hubble, a horse head of a different color, looking at this iconic astronomical object in the infrared instead of the visible light as we normally see it. Just a little overview of what we're going to be talking about today. As we said, this is celebrating Hubble's 23rd anniversary. These observations were made by the Hubble Heritage team, which is a project here at the Institute which strives to find and distribute the aesthetically best images from Hubble, not necessarily for their science content, but for their sheer beauty, quite honestly. And so we'll talk about how we got the data, what the data were, and Jennifer's going to talk about how those data sets were originally processed to produce the images that we use then to reconstruct the color image. And finally, we're going to talk about another part of this project, which was to produce a 3D visualization. So let's have a little bit of context. The Horsehead Nebula sits in the constellation Orion, as we see it in the sky. This is one of the most recognizable constellations in the sky, and it appears most prominently in the wintertime, when coincidentally, at least in the northern hemisphere, the skies are nice and clear, and we can see all the beautiful stuff that's in the Orion constellation. As it turns out, there's a huge amount of stuff that's going on as we look out towards this constellation. There's an entire complex of material out there. The Horsehead Nebula is one small part of it, and this has been studied extensively. It includes the giant Great Nebula in Orion, also known as M42, which has a cluster of stars embedded in it that they're powering this thing, and lots of other things going on in this. But today we're going to concentrate on the Horsehead Nebula, which is one portion of this. Here's a beautiful image from David Malin, who has been making color pictures, astronomical images for many, many decades. Really the originator of producing color pictures from scientific astronomical data, going back quite a ways. And he produced this image some time ago of the Horsehead Nebula region. And as you can see, there's a lot of other stuff going on. So this pinkish area is emission from hydrogen gas. There's a brighter area. There's some very bright stars nearby. There's a brighter area just above where the Horsehead is, and that's a region of active star formation. There are new stars being formed there. But again, we'll zoom farther in to the Horsehead itself, and here's another nice image from an accomplished astrophotographer named Adam Block, who works out in Arizona.
Now, Zol,
yes.
You just almost called him an amateur, right? But you corrected yourself because that's the traditional name for them. There's amateur astronomers, right. But these guys are so professional at what they do.
Well, also Adam has a concerted outreach effort, and he collaborates with Kitt Peak National Observatory and other observatories, and he does a lot of really high-end astronomical imaging. So yeah, I'm hard-pressed to call people like that amateurs. They may not be doing real research, scientific research, or writing scientific papers, but they're doing very, very high-end imaging work, and there's a number of people like that. So
I just have to agree because I have to agree because it sort of sticks in my craw every time I say amateur astrophotographer when these guys are just so professional at what they do.
So on the other side of the frame here, we see what's labeled an HST WIFPIC 2 image. So a number of years ago, the Hubble Heritage project actually had a public poll, and we asked the public which astronomical object would they like Hubble to look at, and by a pretty wide margin, the poll returned that people would like to look at the Horsehead Nebula, which a lot of people know about. It's a very famous object in astronomy. Everybody looks at it, and so we actually took those observations. As it turns out, Hubble, with that camera at the time, this was in 2001, got a pretty nice image, although it's not the best image we've done, as it turns out. Although, if you compare these two images, you can see that the Hubble image, we see a fair amount more detail. The structures that we see are more, they're finer structures. So this is evidence of the better resolution that Hubble has, primarily because it's above the atmosphere, than ground-based, even the best ground-based telescopes can see. So the other thing about this image is that it's in one filter. It's in the light of hydrogen. So hydrogen atoms are emitting light, and this filter in the camera is tuned to the wavelength of that light, and that's what we're looking at here. So we see a dark object against a fairly bright field surrounding it. Now we actually did take images in other filters, some broadband filters, to get a color image. We produced this color image with WIFPIC 2 back in 2001. This was the Hubble Heritage image of the Horsehead. And again, you can see that there's a fair amount of detail there. We see a bright object at the top, sort of at the forehead of the horse. And this is a star that's embedded in the nebula. So this was essentially the best image we could get of the Horsehead at the time. Now you notice the colors are a little bit different. We chose to assign colors in a way that was a little bit different because the selection of filters that we had is a little bit different from the normal view of the Horsehead that you normally get, which is mostly red because it's mostly hydrogen light emission, which is primarily in the red. So just so going on, now in 2013, actually in 2009, a new camera was installed on Hubble called Wide Field Camera 3, and this actually incorporates two separate cameras. One is a visible light camera. It also is sensitive a little bit into the infrared and a little bit into the ultraviolet. So the infrared is light that's redder than the reddest light that humans can see, and ultraviolet is light that's bluer or higher frequency, higher energy, if you will, light than the bluest light the human eye can see. But in addition, there's a infrared light camera that's only sensitive to infrared light, and this is beyond the sensitivity in the infrared that the visible light camera can see. So we decided to redo the Horsehead image in infrared light. And in fact, we were somewhat prompted in this and encouraged in this by seeing this image, which is a ground-based image taken in infrared light by a telescope of the European Southern Observatory. This telescope is called VISTA, and that acronym is currently escaping me, but it's it's an infrared camera on a large ground-based telescope. And the interesting thing about this is that we can start to see how different this area looks in the infrared as opposed to visible light. We see this very bright nebulosity in the center left of the image, which we'd seen in that David Malin image as again, a very bright patch, very active region of very active star formation. And toward the upper right, we can see a sort of ghostly head sticking out, and that in fact is the Horsehead Nebula.
All right, so Zolt, the acronym is Visible and Infrared Survey Telescope for Astronomy.
There you go.
That's what VISTA stands for. Okay. On to the next one.
Okay, so actually, I'm going to actually hand it over now to Jennifer, and I will just say that, so Hubble Heritage is a program, again, to locate and distribute the visually best images from Hubble. Now, in the process of this, we've been very fortunate to actually have a little bit of time on the telescope that directors of this institute have agreed to award a little bit of time to Heritage to be able to make our own observations. Now, some of these observations are intended to augment existing data in the archive. Some data sets in the archive which were designed for obtaining science with a little bit more observation can in fact make a much nicer image. So we have some time to make those observations. Now, in some cases, we will produce images without any previous data in the archive, and this Horsehead image is one of those. In addition, this was intended to commemorate, as we said, the anniversary of Hubble's launch, and we have done that numerous times. So we've been able to use this telescope time to take images which we then release as a commemoration of the anniversary, and that's what we did this time. So we designed these observations and got the data, and Jennifer is going to talk about how those data were initially processed. So take it away, Jennifer.
Hi, thanks, Zolt.
Okay.
So, should I go ahead?
Yes, go ahead.
Okay, hi. So I'm going to give you a bit of a behind-the-scenes look at how one designs an observing program with Hubble. And then I'll show you what raw images look like coming down directly from the telescope, how they look as they pass through our different stages of our calibration pipeline, and then how I do some manual work to really stitch the images together to form the larger mosaic in the two different filters. So I will go ahead and start sharing my screen here. Okay, so this actually is a ground-based image, which is what we start with, and we take the infrared camera footprint and we overlay it onto the image to try to figure out where we will be observing. This is our planning tool for scheduling observations. So there's the infrared camera, and as you can see, it's quite a bit smaller than the actual Horsehead itself. And so what we will do is move the camera around and then stitch the individual exposures together to create the larger mosaic. Now, actually, all of Hubble's cameras have populations of pixels that are either unstable or have poor response to light. And so we do a little trick by taking that first frame, and then we do a small shift. So you can see here I'm blinking back and forth. We've shifted the telescope by a small amount, and what we can then do is use the shifted image to replace the pixels that were bad in the first image, so that therefore then we kind of correct those artifacts. And I'll talk more about that later when I show the actual images. So then we step the telescope around, and this is the full 3x3 mosaic that we created, which consists of 18 images in the infrared. Now, Hubble actually has several operational cameras on the telescope right now, and so for this program we actually turned on the advanced camera for surveys as well, and that sees light in the visible part of the spectrum as opposed to this infrared light. And so these are actually called parallel observations, which is essentially turning both cameras on at once, and it gives us a freebie image of the pink squares that are just to the right of the Horsehead. And so this data actually will be released very soon. For now, we'll just focus on the infrared observations. So Hubble's observing schedule is actually created a week at a time. So once this program was ready to go, we uploaded all the commands to this telescope, and the data were executed, and then we get the images back from the telescope. And if you've ever wondered, what does a raw infrared image look like that comes back? When I first looked at this one, I said, I don't see any Horsehead here. Where is it? Well, I'll go to the next image, which is the same 44-second image, but now signal from the detector electronics has been removed. And so you can see that there's a couple of bright stars in the image which show through in the raw image, and they're also in this calibrated image. But you can now see in the lower right corner the top part of the Horsehead, and in addition, numerous stars and galaxies in the background of the sky itself. So,
Jennifer, that's kind of amazing that the detector. It looks like you're pulling signal out of nothing. Pulling something out of the air there.
yes, so it's actually a fairly simple just subtraction of the detector electronics. We do this calibration to figure out what that response is, and we just subtract that right out, and bam, here comes the image.
I think that's amazing for a lot of our viewers to see that for the first time.
Yeah. So, and now this image is actually a subsample of 16 sub-images which make up the full exposure. And this is the full exposure, which is a 12-minute stack. And the primary difference here, I'm going to blink between the two, you may be able to see there's populations of bright white pixels which go away when we do the stack. Those are actually high energy particles from the sun called cosmic rays. And so with this stack, we're able to remove those cosmic rays. And next, this is a further combination down the path. we take the two pairs of images that have been slightly shifted, we correct for geometric distortion of the camera. It sounds very technical here. But what you'll notice is that what started out as a square-looking image now becomes more rectangular. And what we do is we take out geometric distortion, which ends up making all of the pixels equal area on the sky. In addition, you may be able to see this, but there's still some white pixels in this stacked image, and those are actually bad detector pixels. And so when I talked about how we shift the telescope by a small amount, we can actually fill those in from the second exposure, and we get this higher signal-to-noise combined image. All right, so next. Now this is an image where I just take all of the 9 individual tiles and put them together with a new software we have here called AstroDrizzle, which takes out the distortion and it knows about where we pointed the telescope and it tries to put them all together. And it's a 3.5 hour combined exposure, and you will notice the first thing that jumps out is it's not really continuous across the image. There's offsets in how it's estimated the sky background, and so I actually go in and measure the sky and take that out. So we have, this is the final nice combined image in, I believe this is the F160W filter. And this is the corresponding exposure time map. So just to go back to the original planning of the observations, you can see how this is stitched together from 9 individual pointings. And you can also see the black little circles here are regions on the detector which have poor response to light. And so we do this shift so that we can fill those in the final image. So you get a nice clean composite. And now we do one other little trick. The white images, or sorry, the white regions are actually regions of higher exposure time. So that's where there's overlap between the tiles. And we can use stars and galaxies that fall in those regions to solve for any remaining shifts between the images. So really to just kind of fine tune, it's like tightening a wheel. You kind of tighten up the alignment and get this thing together a little bit better. So I'm actually going to zoom in here to the region that's shown in the blue box. It'll show you the overlap regions in the upper right corner of the mosaic. And so this is what it looks like in that stacked image, and I'm going to blink with the one after I've aligned, after I've fine-tuned the alignment. So I'm not sure if how this shows up out there for the viewers, but what you end up seeing is there's some shifts in between the little squares, and in addition I've circled in blue some little sources. Some of those are stars and galaxies. Those are the ones that we use to correct the alignment. And in the original image, those were actually rejected. The software identified them as bad pixels because they were there in one but not in the other. But then when we get the alignment correct, then they all pop back in. And so that's kind of the behind the scenes on how do you create these large mosaics. And I just wanted to advertise that all of this processing now is resulted in these high-level data products. And these are available for the public. They're available for anyone who'd like to go in, grab the FITS images. For these advanced image processors, you can go in and get the 2 filter images, and you can make your own color composite. Or for scientists who want to go in and actually do science, this is the first release of this data. It's available for anyone who wants to do science research on this target right now. And we're very excited to make this available to the public. And additionally, another thing you can do is when you get the individual filter images, you can play with the dynamic range and look at things like focus in on the background galaxies, zoom right up to the Horsehead and look at the fine details of the filamentary dust and gas features. And it's just absolutely a beautiful data set. So I'd encourage anybody who wants to go to our archive and grab these data. So I'll hand it over to Zolt, who will be showing how you take those two filter images now and create a color composite.
All right. Thanks, Jennifer. Really appreciate that. And this is just a phenomenal data set. So I will go back to my little presentation here. Start that back up. Okay. And so Jennifer showed basically went through the process for one image, but we actually took data through two different filters. These are both infrared filters in the infrared from the infrared camera. So these are the two nicely composited, nicely mosaicked data sets that we ended up with. And so one of the, there, as I said, two filters in the infrared. One is 1.1 microns, and the other is 1.6 microns. So they're not too far apart in terms of wavelength, but they, as you might see, they do show slightly different things. And but our goal was to produce a color image, and so using these two data sets, we can produce a color image. Now, normally we use three images because we normally work with a three-color visual model, and we use the three primary colors: red, green, and blue. And using those three primary colors and the ratios in the brightness at any pixel in those three colors determines the final color of the image. And you can, from those three colors, you can construct essentially any color that we can see. Now in this case, we only had two filters to work with, and so we used two colors. Now if we use two complementary colors, in this case blue and red, to assign to the black and white images, those will also add to white, to gray. So, so this is what we did. We assigned a color to each filter image. We assigned blue to the 1.1 micron image and red to the 1.6 micron image, which is a longer wavelength, a redder color. Now we're talking about infrared light here, light that we cannot see. But there are still colors within the infrared, in a sense. There are different wavelengths. The different wavelengths of visible light produce the different colors for our perception. And in the same way, in the infrared, there are different wavelengths of light, in essence, different colors, even though we can't perceive them. But we can produce a multicolor image in the infrared just like we can produce a multicolor image in the visible. So that's what we did. Again, we assigned blue to the shorter wavelength image and red to the longer wavelength image. We composite those two images together in a way which blends them, and this is the result we come up with. You can see there's a range of colors. There's some stuff that looks bluer and some stuff that looks redder because we have a red image and a blue image. It's a little bit pale and very ghostly. And the first thing we notice when we look at this image is that it's kind of a negative of the visible light image. I'll say a little bit more about that later. I want to talk a little bit more about the technical stuff about putting the image together. So again, this is the kind of first draft of the image as we first see it when we composite the two color filter images together. We can apply some adjustments. We can adjust the contrast, tweak the color a little bit. And this is more this is more of a final image. We've also cropped it. I'll go back to the previous image. This is the full mosaic image, and you can see, interestingly, that what I often have to marvel at is how precise and repeatable Hubble observations are. So the images in the two filters are at 9 different locations. And in fact, there are dither positions, as Jennifer was describing, so there's actually 18 different positions that the telescope had. But in the two filters, those positions absolutely overlapped. So you can see that the edges are all overlapped in both the images. We cropped off somewhat uneven edges and ended up with this nice rectangular image. So this is our final image, and there's a lot of interesting things we can immediately see in this image. But before I get to that, I want to talk, and one of the things we do, aside from color adjustments and contrast adjustments and so forth, is sort of clean up the image a little bit, and there are some additional instrumental artifacts that are introduced which don't get taken out by the routine processing that Jennifer was describing. One of which is one of these patches of essentially dead pixels. So at the upper left corner of this slide, you see sort of a almost circular patch of kind of gray and black pixels. This is what the Hubble instrument people have imaginatively called the Death Star, an area on the detector which is the detector doesn't work in that small area. Now, this happens. This is one spot on the detector. So we've taken our 9 fields in the image. That spot is in each of those 9 fields. But fortunately, there was enough overlap. We designed the observations this way, so there was enough overlap in the rest of the image, so that there was a good image to overlap the place where the Death Star was. On this corner, on this edge of the image, there was no other image to overlap there, so it appears. And we didn't want to crop any more of the image off, so we left that spot there. However, we can retouch that with kind of standard rubber stamp or cloning tools. It's in a relatively blank area of the image, so we're pretty sure that there's not anything significant back there. So we essentially retouched it. We retouched it out with no great ill effect. On the right-hand side, you see, on the left-hand side is a single filter image. On the right-hand side is the color composite with all the color compositing and adjustments done, and also with that little patch retouched. On the bottom, yes.
I would just like to point out that the purpose of this is not to change the image, but it is to correct for defects of the observing, so that we want the universe pixels to come through. We're not changing anything to try and play with it. We're really just getting rid of the defects in the observation system.
Right. It's stuff that the telescope and cameras put in, and not what's we're hoping we're not changing anything that's actually out there on the sky. The bottom pair of images is a little bit different. So this shows a piece of the image that's up in the top edge, and you can see a fairly bright star that's right there at the edge of the image on the left-hand side part of the slide, lower left part of the slide. There's a fairly bright star that's right on the edge of the frame. Now, we're not really fond of having stars right at the edge of the frame because they become more distracting than anything else. So we wanted to crop that out. Now, if we crop that out, we're left with these lines on the image, which astronomers call diffraction spikes, which are the result of light bouncing around in the telescope structure and causing this light to appear on the image itself. And again, it's not something that's an obvious part of the star itself. It's part of the result of the optics in the camera, and the telescope rather. So we removed the star, and so we thought we really ought to remove the diffraction spikes as well, since a diffraction spike without a star is pretty weird. So we went ahead and took those diffraction spikes out. We really didn't have to do very much else. This was really a very, very clean image. So now I'd like to concentrate a little bit on what we're seeing in this amazing image. So here's a comparison between our 2001 WIFBIC2 image on the left and our brand new WIFC3 image, infrared image on the right. So again, the image on the left was made in visible light, and the image on the right is made in infrared light. So immediately you can see there's a big difference in the sense that almost everything that's dark in the visible light image is bright in the infrared light image, except for the stars. Now, there aren't as many stars visible in the visible light image, which is one of the other major differences. So we see a lot more stars, and that's primarily because the starlight, the visible starlight, is being absorbed by the dust. That's the relatively dense dust in this region, which is causing this whole appearance of this object. Also, again, the darkest areas of the nebula are actually in the visible are brighter in the infrared. Another, because we're seeing the glow of that dust, whereas in the visible, the dust is absorbing all the light that's coming from behind it. And also in the top part of the image, you see that it's very bright in the visible light and very dark in the infrared. In fact, it's entirely transparent in the infrared. What we're seeing on the top part of the image in the infrared light is seeing straight through this nebular region, this region of fairly dense gas and dust. We're seeing right through it, and we're seeing stars, but we're also seeing very distant galaxies. In fact, I believe I have another slide which zooms farther in, and you can see these galaxies very clearly. There's nice little spirals, and actually they're large galaxies, just like our own. They're giant galaxies, but they're very, very far away, so they look tiny. We're seeing face-on spirals. We're seeing edge-on spirals. We're probably seeing a few ellipticals here and there. And in fact, it's a pretty dense region of galaxies. I'm wondering if it's even a cluster of galaxies. So
I would just add that this is actually also kind of analogous to the Hubble Deep Field images, where they look at a blank part of the sky and these little baby galaxies from early in the universe, the light just comes through. So since we have this kind of deep exposure, this is light from the universe really in its infancy that's coming through behind the Horsehead.
Yes, and you have to remember too that this is infrared light, so we're seeing light that's a little bit different from the usual deep images. But in fact, that's true. Almost every fairly long exposure with Hubble, you see this field of galaxies back there. So that's really what the universe looks like back there. There are places like the Orion region where in visible light this is primarily obscured. We don't see this at all. But now in the infrared, it becomes transparent. We can see this background, background galaxies. So the last thing we kind of want to talk about was a 3D visualization that we made, and this is playing. This is a little movie of this visualization that we made. So we have no actual information, numerical information about what them looks like in the third dimension. However, we have some pretty good ideas by looking at the image and kind of understanding what this area is in fact. We have a pretty good idea what this should look like in the third dimension. So what we've done is produce this visualization with 3D modeling techniques combined with the actual image and produce this visualization. So Frank, would you like to talk a little bit more about how we produce this and some of the background for this?
Okay, but I'm going to use your slides, right?
Yes. So let me go back to this. Right.
So why don't you...
So do we want to go to the next slide, or we want to play this again?
Yeah, let's go to the next slide.
Okay.
Or you can try playing it again. What I'll do is
playing.
Is it playing?
It's playing.
I lost it on...
Uh-oh.
I see it.
Okay.
I don't see it. Zolt, I've got your... There we go. Now it's back up.
Okay. Well, let's go to the next slide.
Okay, so you can see it plays a little steppy here. I will post the URL on the Hangout page, so you can go to the Hubble site website and download it. So this is the 3D visualization broken apart into planes. Our group here with Zolt, myself, Greg Bacon, Lisa Fratari, Tiffany Davis, we've been doing this ever since the IMAX film Hubble 3D, where we had to create these stereo 3D visualizations for an IMAX screen. And one of the simplest ways to do stereo 3D is what we call decoupage 3D. If you remember the old decoupages, which were these physical images that were cut out and then stacked on top of each other to give the illusion of 3D, well, we do the same sort of thing in a computer. And so you can see the 1, 2, 3, 4, 5, 6 different planes we have here, various objects in the Horsehead. The foreground plane is stars, which we'll talk about in a second. The background plane is galaxies, which are put in at a huge distance. But the other planes are pieces of the Horsehead Nebula itself. We've analyzed the Horsehead Nebula scientifically to try and figure out what's in front of what pieces are slightly separated from each other, and then Zolt and Lisa, our image processors extraordinaire, will go through and mask those images out, and we'll pull those out into separate layers. Then we take those layers, and if we go on to the next slide, Zolt, can we go on to the next slide?
I have gone on to the next slide.
Oh, I'm not seeing it on.
Uh-oh.
There we go. Now I'm seeing it.
Okay. A little bit of a delay.
That's all right. So, in the we take them into a 3D modeling program, and then we actually sculpt these objects to the scientific ideas of their three-dimensional shape. So we have multiple layers inside our computer graphics model, and each of those layers is then sculpted in 3D with those layers placed, slightly in front or slightly behind each other to give the full 3D effect. You can also see at over on the right-hand side of the screen, midway up, you can see the virtual camera, which then flies through this the 3D model. Okay, let's go on to the next slide. And it'll probably take a few seconds for me to see it. There we go, much faster this time. Good. All right, now you can see the camera's in roughly the same spot, and we've done the texture map of the nebula. But what's in green there are all these tiny little rectangles. These are the individual stars that have been cut out of the image. We showed them as a single plane in the beginning, but actually we took that single plane, we took some scientific software called Source Extractor, analyzed the image, found where each one of those stars was, cut out a tiny postage stamp around it, and then placed those stars in 3 dimensions around the nebula. Now again, we don't know the exact 3D positions for each one of these stars, so what we've done is we've...
Sorry.
Yeah?
Sorry. I changed the slide when I didn't mean to.
Oh, I didn't. Okay. It hadn't changed on my screen yet. Okay, and so we use a statistical model to place these stars around in front of the nebula. Now, a couple of these stars we knew were really close to the nebula, especially that one star at the very top of the Horsehead. So we went in by hand and placed that where we thought it most likely existed, and a couple other stars that had some red coloring to them that you could tell are getting just on the surface of the gas of the nebula. We could place those by hand. The other ones were placed mostly with a statistical model to keep them close to the nebula. This is just a subset of the stars shown in this image. There were a lot more stars wider that could actually be distributed in the foreground and then also in the background. So we have one more slide, Zolt?
Yes. If you don't have any more to say about the 3D stuff?
No, I just I'll tell them that I'll post the URL on the page right now. Oh, by the way, I've also posted there was somebody who made a wonderful comment about how incredible to see both visible and infrared. I posted an animated GIF of the visible to infrared on the page, and I'll post the URL for the movie right now. So back to you, Zolt.
Thanks. I really just wanted to, before wrapping up, I really just wanted to mention that a shameless plug for our follow-on mission, the James Webb Space Telescope. And this image that we're talking about today, this infrared image of the Horsehead, is really kind of a preview of what we're expecting to see with James Webb. So James Webb is a scientific follow-on to the Hubble Space Telescope, and it will continue the exploration that Hubble has done, and more deeply and more extensively. And to do that really requires it to be an infrared instrument. So James Webb will operate entirely in the infrared, and we will see stuff very similar to what we're seeing today with the Horsehead. Only we'll see, all the kinds of things that Hubble has been looking at over its now 23-year lifetime. James Webb will be looking at in the infrared and hoping to see the very, very farthest things away that we can detect in the universe, and lots of other cool stuff. So this is a nice preview to what James Webb will do. And then I just had one final kind of summary slide, which recapitulates what we've been talking about. That we're seeing this nice infrared image taken with Hubble Space Telescope. It was done in commemoration for Hubble's 23rd anniversary, using observations planned and executed by the Hubble Heritage program, which hopes to find the visually best images. We produced a color composite image from those data and produced a 3D visualization. And I think that's it.
Well, that's fantastic, Zolt. I'm going to come back to myself for a second and ask a couple questions of you, Zolt, if you want to get rid of your screen so we can see your face.
I will do that.
Actually, Jennifer, let me ask you first. When you were giving your presentation, I noticed that there were, you said 18 different pointings, but then we had 2 filters. So we're really talking like 36 different observations with Hubble? And what's the resolution?
Yes, 36 in the infrared, and then 36 actually parallel observations taken with the advanced camera. Well, actually, no, that's not quite right. There's 18 with the advanced camera. We kept the same filter with the advanced camera, whereas for the infrared detector, we switched between filters. So yes, there's 36 for the infrared, and there's 18 in the advanced camera visible light image.
Okay, and then what's the resolution of each of those observations? So what's the total number of pixels we really have on this image?
Well, the infrared camera is about 1,000 pixels across. So you take 3 of those, so it's about 3,000 by 3,000. And each pixel is about 0.1 arc seconds. I think the full, if you want to do it in light years, it's about 2.5 light years across the full mosaic.
Okay, and let me just point out for the people listening that on our website, the full resolution image that we have for you to download is 2,704 pixels by 2,826 pixels. So we aren't hiding a single pixel from you. You get to see every single pixel that Jennifer's team took.
We cut off, as I mentioned, we cut off a little bit on the edges to clean up that slightly ragged edge, and there's some overlap, so that's why we don't have the full extent of 3 or 9 times 1,000 pixels. But
right, but if you go to the archive, you can get the full thing. Yes. And Zolt says they cleaned up some things. Well, those are just at the edges because, as I said, we did this strategy where we shifted the telescope, and we've actually filled in all these these regions. So if you get these images, they are pristine, beautiful, just extraordinary, high-quality products. So I would encourage you to, if you're interested, go get them.
Okay, so that's like over 7.5 million pixels for you to look at. And Zolt, I had a question for you. You mentioned the Hubble Heritage Project.
Yes.
Just how many images has the Heritage Project done over the years? How long has it been going? Tell a little bit more about that.
The Heritage Project was established in 1998, quite a while ago now, back when our primary camera was Wide Field Planetary Camera 2 with BIC 2. And it was started by a small group of astronomers here at the Institute who felt that while it was good for the science results to get out from the telescope, they felt that the images were such high quality and so aesthetically beautiful that we really needed a concerted effort to really showcase the really most beautiful images from Hubble. And so that's what we've been doing ever since then. Nominally, we put out 1 image a month, so you can do the math. 1 a month since 1998, that's a couple hundred images. So if you go to heritage.stsci.edu. You will see every single one of our images, along with some ancillary information, some more in-depth discussion of, it varies from release to release, what we highlight there. We highlight some of the science, we highlight how we put the images together, we highlight the people involved. Sometimes we will highlight a scientist that was involved with these observations or the science behind the observations. Sometimes we'll highlight a team member or somebody else that may have had something to do with what we're releasing. So it's a pretty varied bunch of stuff out there, and we try to have a different angle on it than the science, kind of newsy science releases that we also do.
And I think that it shows off the fact that, that we here at the Space Telescope Science Institute, we know that we're doing this for research science, but we still appreciate that it has such incredible artistic beauty that we can't help but get that kind of those kind of images out to the public. All right, there was one question here on the website that says, I read something that a science writer recently wrote referring to the Horsehead as a pimple. And well, let me just say that I don't think that pimple is the right term for it, because when you think of a pimple is growing out of the skin. Let me get my hands into the you think of a pimple that's growing up. Well, actually, what this is this is being eroded away. The light from the bright star Sigma Orionis, which is above the Horsehead, is actually eating away the gas. The high energy radiation, ultraviolet radiation, is ionizing the gas and causing eating away at the lesser gas, lower density gas, and the higher density gas is remaining, which is what you see in the Horsehead. So that dark silhouette is the denser gas that's resisting the erosion from Sigma Orionis. Did you want to add something, Zol?
Yeah, I think what they might be referring to is kind of coincident with our image. An image was released by the Herschel telescope, which is a telescope that's dedicated to looking in the infrared. Now, Herschel has a much wider field of view than Hubble does. So it's at any one spot, the resolution is lower than what Hubble can see, but it can see in one exposure a much wider area of sky. So they also released an image of the Orion region, but it's a much wider area, and you see a huge amount of this glowing stuff glowing in the infrared. And off in the corner, you see this little blip on the side, and that's the Horsehead Nebula. And the neat thing about that to me is that, yeah, and it kind of looks like a pimple on this giant cloud of gas. But the neat thing to me is it's how complementary it is with our image, that we're able to really zoom in and see this little area, well, relatively little area. In our field of view of the sky, it's a tiny little piece. In reality, it's this gigantic multi-light-year across thing. But if you look at the Herschel image, you see this really large, really complex region, and it's really impressive. So it's this nice complementarity between different astronomical observatories.
I would agree with you, and that leads me to the last thing we want to end with, is that the Horsehead Nebula is a temporary structure. Because it's being eroded by the ultraviolet radiation from Sigma Orionis, folks have estimated that it will actually disappear in about 5 million years. So you can be glad we've got Hubble up there to take those observations now, because 5 million years from now we won't have the Horsehead Nebula. Of course, we'll have other beautiful structures to look at that time, and the telescopes of that time will have probably take much more amazing images. All right, any last thoughts from you, Jennifer?
Just, I think it's neat how we can look out into space and kind of identify patterns or things that look familiar to us, like a horse's head. I mean, there's nothing really in particular, particularly that different about this part of the part of the sky than the surrounding regions. It just so happens that it sparks our imagination and makes us think of something familiar, like a horse's head, and it gets people excited, and it's just it was just a really fun set of observations to be a part of.
All right, thank you very much. And thank you, Zolt. Do you have any last comment, or
No, I
you
think
commented out?
I think Jennifer's comment was right on the money, and really appreciate it. We didn't really talk about why we call this thing the Horsehead, so that kind of explains it.
Okay. All right. Thank you all for attending this Hubble Hangout on the 24th anniversary of Hubble. And we look forward to bringing more Hubble Hangouts to you. I apologize for the technical difficulties at the beginning, but
My fault.
Zolt had a few technical problems, and Tony Darnell, who has hosted these before and was supposed to host this one, is on vacation, so I had to learn how to host it, and we'll do much better next time. All right, thank you all for coming, and keep looking up. Take care. Bye.
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 All right. Hello, everybody. The broadcast is said to be live now. I hope it's recording well. I am Dr. Frank Summers of the Space Telescope Science Institute, and it is my pleasure to welcome you to celebrating 23 years of the Hubble Space Telescope. We had we have some amazing things, and let me just show you a couple things. What we're celebrating is that 23 years ago, this was the launch of the Hubble Space Telescope on the shuttle mission STS-31. And you'll notice that not only do we have Hubble launching on Discovery here, we also had just happened to have another shuttle on the launch pad doing some testing, and then a day later we had Hubble was deployed by the astronauts of STS-31, and we have 23 years of amazing history of images, and today we are going to discuss the image that we released Friday morning, sorry, an infrared view of the Horsehead Nebula. This is the image here, and this is the amazing image that the experts who processed it will tell you all about it. So let me stop my screen share. There we go. And introduce the experts who are going to talk about it. Our first expert here today I'm going to introduce is Mr. Zolt LeVay. And Zolt, why don't you tell them a bit about your history here, what you do at Space Telescope.
Okay, thanks, Frank, and welcome everybody. A cluster of stars embedded in it that they're powering this thing, and lots of other things going on in this. Well, today we're going to concentrate on the Horsehead Nebula, which is one portion of this. Here's a beautiful image from David Malin, who has been making color pictures, astronomical images for many, many decades. Really the originator of producing color pictures from scientific astronomical data going back quite a ways. And he produced this image some time ago of the Horsehead Nebula region. And as you can see, there's a lot of other stuff going on. So this pinkish area is emission from hydrogen gas. There's a brighter area. There's some very bright stars nearby. There's a brighter area just above where the Horsehead is, and that's a region of active star formation. There are new stars being formed there. But again, we'll zoom farther in to the Horsehead itself, and here's another nice image from an accomplished astrophotographer named Adam Block, who works out in Arizona.
Now, Zolt?
Yes.
You just almost called him an amateur, right? But you corrected yourself because that's the traditional name for them. There's amateur astronomers, right. But these guys are so professional at what they do.
Well, also Adam has a concerted outreach effort, and he collaborates with Kitt Peak National Observatory and other observatories, and he does a lot of really high-end astronomical imaging. So yeah, I'm hard-pressed to call people like that amateurs. They may not be doing real research, scientific research, or writing scientific papers, but they're doing very, very high-end imaging work, and there's a number of people like that. So
I just have to agree because
and happy birthday, Hubble, and happy Earth Day. all those things. So I started here at Space Telescope Science Institute quite a long time ago, about 30 years ago. And for the last many years, I've been producing images from Hubble data. So that's kind of what we do. We use the same data that the astronomers use and have produced quite a number of nice, colorful images to distribute to the public to demonstrate what Hubble's doing, to announce the science discoveries from Hubble. And I'll turn it over to Jennifer Mack.
Hi, I'm Jennifer, and I've been at the Institute here for about 16 years. I do both science research and instrument calibration for the telescope, and I'm a member of the Wide Field Camera 3 team. That's the camera that was used to make the observations that were made today, that we're presenting today. And so I'll be giving you a bit of a more technical view of behind the scenes. How do we take these images that come down from the telescope, raw images, and put them in together to then create this beautiful color composite that you see in the news.
Right. And so as you can see, we're going to be taking you, not just give you the pretty picture overview, but we're going to give you the technical behind the scenes of how these images really are put together. So Zolt has put together a PowerPoint presentation. So if he'll turn on his screen share, we'll go back to Zolt. And Zolt, take it away. Tell them all the cool stuff.
Okay, thanks, Frank. And I'll get my thing started here. I will start the slides. So as Frank mentioned, we're talking today about this new image from...
I have to agree, because it sort of sticks in my craw every time I say amateur astrophotographer, when these guys are just so professional at what they do.
So on the other side of the frame here, we see what's labeled an HST WIFPIC 2 image. So a number of years ago, the Hubble Heritage project actually had a public poll, and we asked the public which astronomical object would they like Hubble to look at, and by a pretty wide margin, the poll returned that people would like to look at the Horsehead Nebula, which a lot of people know about. It's a very famous object in astronomy. You know, everybody looks at it. And so we actually took those observations. As it turns out, Hubble, with that camera at the time, this was in 2001, got a pretty nice image, although it's not the best image we've done, as it turns out. Although, if you compare these two images, you can see that the Hubble image, we see a fair amount more detail. The structures that we see are more, they're finer structures. So this is evidence of the better resolution that Hubble has, primarily because it's above the atmosphere, than ground-based, even the best ground-based telescopes can see. So the other thing about this image is that it's in one filter. It's in the light of hydrogen. So hydrogen atoms are emitting light, and this filter in the camera is tuned to the wavelength of that light, and that's what we're looking at here. So we see a dark object against a fairly bright field surrounding it. Now we actually did take images in other filters, some broadband filters, to get a color image. We produced this color image, Hubble, a Horsehead of a different color, looking at this iconic astronomical object in the infrared instead of the visible light as we normally see it. Just a little overview of what we're going to be talking about today. As we said, this is celebrating Hubble's 23rd anniversary. These observations were made by the Hubble Heritage team, which is a project here at the Institute which strives to find and distribute the aesthetically best images from Hubble, not necessarily for their science content, but for their sheer beauty, quite honestly. And so we'll talk about how we got the data, what the data were, and Jennifer's going to talk about how those data sets were originally processed to produce the images that we use then to reconstruct the color image. And finally, we're going to talk about another part of this project, which was to produce a 3D visualization. So let's have a little bit of context. The Horsehead Nebula sits in the constellation Orion, as we see it in the sky. This is one of the most recognizable constellations in the sky, and it appears most prominently in the wintertime. When coincidentally, at least in the northern hemisphere, the skies are nice and clear, and we can see all the beautiful stuff that's in the Orion constellation. As it turns out, there's a huge amount of stuff that's going on as we look out towards this constellation. There's an entire complex of material out there. The Horsehead Nebula is one small part of it, and this has been studied extensively. It includes the giant Great Nebula in Orion, also known as M42, which has